interior mapping. That's the subject that we're going to talk today's tutorial. So even if you played or saw the gameplays of the Spider-Man game, you might notice that there are 3D building interiors when you look through the windows of each room. But they're not actually real. They are actually faked using shaders. And we will try to achieve a similar effect with shader graph. But in the tutorial, we will look to this technique in 3 steps. In the first step, we're gonna look what is actually interior mapping and where it is used. And in the second step, we're gonna look at the interior mechanism, like how it works, how it can be applied in our case. And in the third step, we're gonna jump to the shader graph and try to create the same effect. Step 1, let's start with the definition. You might be asking, what is the interior mapping anyways, right? It is a technique which is widely used in the game industry for decades. And you might saw it in old BioShock games or the Spider-Man game or Crackdown games or many others. Or even SimCity. So the technique is originally published by this guy, and you can access to the white paper from the description box below as well. I will add the link if you want to look to more technical explanation. But in terms of the definition, this interior mapping is simulating parallax corrected fake environments. In reality, you don't want to have each and every one of room interiors in reality. Like, you don't want to have 3D drawn meshes, because if you do, and if you have multiple rooms, it'll create a huge overhead in your performance, because each one of those objects, furniture, rooms, anything, they need to be drawn and taken care of by GPU and CPU, or like your render pipeline, and it will slow you down a lot. And if you have those fake interiors with not prior, like if they're just gonna look from a distance, or like player will not gonna interact with them, generally game developers are using printed textures to the windows. So in the GTA 4, if you look at it, you'll see most of the windows doesn't have anything. Like they just like the sticker printed out to the window, and it breaks the immersion. I'm telling you this because even if you are developing for mobile platforms or consoles or high-end devices, this technique is not performance hungry and can be used even in the Nintendo Switch. So this technique creates an illusion of the virtual room, and using the mechanism that we're going to explain in the step 2, it will give the immersion and the 3D feeling to you when you look through the window, with also keeping the performance cost very low. That brings us to the second step, step 2. So let's take a look at the inner mechanism, how it works. I strongly recommend you to take a look at the paper that I will attach to the description box, but we will briefly explain the inner mechanism of it. Let's say we need to have a virtual environment, but we don't want to draw it because the player will not interact with the environment in reality. But if we don't put it, it will look really non-immersed, like it will look fake. And we don't want that. Even if you all have a cartoonish art style, it's an important thing. You don't have to have super realistic graphics or stuff. It'll create the immersion to your world, to your simulation, your environment. It's not related to create realistic graphics, but believable and not uncanny valley kind of graphics. So to do so, we need to start with simulating a virtual room in our case. But also this technique can be applied to other cases such as cars or anything that has interior. But we're going to talk to the rooms first. In the rooms, you need to simulate a room environment, you know, like a box. It can be a unit box, which is more convenient to be able to map the cube map or texture atlas into it. And then, considering the fact that you have created that virtual room with not the mesh, just simulating it, the boundaries, let's say, and then using the window, the real window mesh, and the camera, you will cast a ray from the camera through the window, and then this ray will pass through the window to our virtual room, and it will intersect with the virtual room's ceiling or the walls, wherever you're looking at, with many different rays. And then we need to scale the dimensions of the cube map, remap it, so to say, with our virtual room. And then when we do that, we can actually get the pixel, that pixel of that texture belongs to that intersection point, and then get that back and put it into the window in wherever you look. It's just pretty similar to what we do in the real life, and it's really easy to implement as well. That brings us to step 3, the implementation. Let's jump to the shader graph and find out more. So we need to start with creating a view direction first. So view direction node is important because we're going to rely on the view direction of the camera, but we will not stick with the world space. The reason behind we will not stick with the world space or the object space is simple, but in the actual paper it was suggested to use one of those spaces. But problem occurs when you have curved walls or furniture which is not shaped like, you know, cubes. If you're not making Minecraft indoors, you're probably gonna need that. We're gonna transfer our space to something called tangent space. We're gonna need that because tangent space is relative to mesh surface rather than the object or the world space, which will solve our curve problem. The problem is, I didn't mention about it, if you have curved surfaces and use object space or world space, things got distorted in those curves because it's relying on axis aligned box, because that's what we have. But if we use the mesh related and relative space, the curves will look normally and will not be distorted. So we're gonna switch our space to tangent space, and then we're gonna need to multiply this output with another value. So the multiplication gonna happen with -1. So I'm gonna create a vector 1 value and give -1 to it. And then I will attach this to the multiply. After doing that, you might be asking, why do we need to multiply with -1, right? This is because a conversion from OpenGL to DirectX. Like in the DirectX, it's top from the bottom. In the OpenGL, it's bottom from the top. Like the y-axis is inverted. So we need to flip that to, you know, have corrected directions in our mesh. So this multiplied value is actually our tangent view direction. The next step is the creation of the simulation environment. Let's begin with getting window meshes UVs first. As a following operation, I'm creating an exposed property to control the tiling and call it as tiling. And then we're going to add a tiling and offset node in order to create multiple rooms if we ever want to create multiple rooms in a giant building. Then I drag that property to the canvas and use a round node to get integer numbers. Because at tiling, we can have floating point numbers as well, though we should have exact room sizes. This is where round node comes handy and rounds those values into integers. Next, I'm going to create a fraction node and a multiply node with the value of 2. Then I'll subtract this node output from 1. It looks like a weird operation, but this is actually a formula to create that virtual cube shape. So don't be confused, it's just math. With that said, we need to split the result of this vector and only take the walls, ceiling, and the floor of the room. We would like to pass the depth by hand to make minor tweaks on the visual appearance. For this, I'll use a combine node to use x and y axes values as walls and for the ceiling. But I'll pass 1 as room depth to z value. You can play with these values and multiply them based on your cube map's appearance. Alright, so we have created a second part as well, which was simulating this cube environment. So we have it right now here. And let me just regroup those things. Create a group, I'm just going to create a group for them to be able to keep it simplified. In this group, I'll name it as the simulating room. And in the other one, I'm just going to call it as the tangent view. Alright, as we discussed before, we need to do several steps. First one was getting the tangent vector, the view, camera, and then creating the virtual environment. And lastly, we need to make a raycasting from camera using the view direction through that virtual world, virtual environment that we just created. So let's jump to that part. First thing for our raycaster is making a division with tangent view direction. I'm going to create a vector 1 and put value as 1 to upper side of the fraction. Next, according to the explanation from the paper, we're going to get the absolute value of this and also multiply the same fraction with a value. Then we will subtract the absolute value from the multiplication result. Though this multiplication should be done according to our fake room's dimensions, which is possible with getting the output of the combine node and connecting it to the other inputs of the multiply node. Then finally we're gonna need to add a split node to split that vector into pieces. Alright, we have created a bunch of mathematical stuff over there. The reason is we have simulated, we have created a cube or a room, but we don't know which part, which side of it is actually our window, the real window. So this mathematical formula, which is converted to nodes, is allowing us to determine the corners of the room. With using that, we can actually determine which side is the window in momentarily. Let's jump to that and let's do it. I need to get the closest corners to the window. To do so, I use minimum node for each one of those axes. Right, using those two functions, as I said, we created the corners. We determined the corners, the nearest corners to us. This way, we know which is the near corner in x-axis, y-axis, and z-axis. So then, the only thing that we need to do is tracing that ray until this position has been intersected to our virtual root. Let's do that. Okay, we're gonna multiply our view direction vector with our room border planes. Then we're gonna add this value to room borders. This way we can actually get the intersection position throughout the array. As a next step, we need to flip all room borders except the depth, because they are somehow flipped if we don't. But the depth, or let's say z-axis value, is the same, so we'll just multiply it by 1 to leave it just the way it is. Finally, we can sample our cube map. I'm creating a cube map exposed property to be able to attach my cube map from the inspector. Then drag it to canvas and create a cube map sampler. To sample cube map UV positions with the interior mapping technique, I plug our multiplication node output to view their input. Oddly enough, when Unity generates sampling code from shader graph, it creates a weird form of the sampler in the code, which doesn't work. To work around this, we need to attach a 0 value to normal vector.
Right, with doing that, we have actually performed the raycasting. Believe it or not, it's that simple, shader magic. Which means if we plug it to the code, to the albedo or the emission, we will see the effect momentarily. Let's take a look at it.
Okay, I'm just gonna connect this to albedo output of the unlit master node. If you have a PBR master instead of unlit master node, you should put it into the emission field. Then I switch back to the scene view and create a simple quad. Yes, it's just a quad. We'll render the entire interior. Okay, I got a simple interior cube map imported, and if I attach it to my material, ladies and gentlemen, I present you the interior mapping.
Right, we have created the actual part, but to make it believable, we need to blend it with the reflection, because generally when you look through the window, you'll see a reflection of the skybox or the outside exterior environment. Let's do that now.
To add exterior reflection, we need to have an additional cube map in place, which means we need to create another cube map exposed property from the blackboard. Then I just drag it into node canvas and sample a cube map quickly. Though I want to use world space since exterior skybox is not in an object, so it should be world space. So I'm creating a view direction and normal vector nodes and leave their space to world, then attach them into cube map sampler. Next step is giving this reflection much more at the middle of the window, since at the window edges generally not that reflective due to the shadows in the real world. And if we want to work with inside out, we need to use our favorite node, Mr. Fresnel. I add a Fresnel node and keep the power value as 0.7. Then using a 1- node, I can invert the effect to keep things reflective at the middle and dissolve throughout the edges. To do so, I need to multiply the cube with this Fresnel. Then, using a blend node and screen mode blending, we can have the skybox reflection on our window. Although this was the overall reflections, but I want to add one more detail. Generally, when you look to a window from a very fine angle, reflection increases a lot, and that makes things really hard to see. We want to have the same effect to increase the immersion. To do so, I'll create a dot product to limit the reflection to wide view angles. Then attach normal vector and view direction vector to it. Then, using a saturation node, I clamp the dot product between 0 and 1. Lastly, I'll use 1- to invert the effect, since currently it reflects from the middle, not from the sides. But I want additional control over these values. Thus, I create a clamp and a smooth step node to limit the side reflections. With that, we are finally about to be done. I just need to lerp this interior mapping and side reflections. Then, using another lerp node, I'll mix our overall blending to side reflection fade out. Finally, I plug that lerp output back to albedo, and congrats! You have completed your fully functional fake interior shader.
Right, with doing that, we have actually created the entire thing. So that's all for this tutorial. I hope you like it. If you do, please consider to be a subscriber to channel from here, or
if you like this tutorial and see more like that, please press the like button, and you can share this video with your friends that want to create interiors like this as well. That's all for this one. I'll see you in the next tutorial.